Hi everyone. Today I'll use a simple physical model to illustrate a key networking concept. The model we are using is shown here in the picture. It comprises of a weight hanging here at the bottom from a system of springs and strings. The two long strings, one here at the bottom and one here at the top, are both not taut. So they don't have tension and the weights right now not hanging off of them. The two springs, on the other hand, this one here and this spring at the bottom here, are both with some tension, together with some tension in this string between the two springs connecting them to each other. So there's a tiny piece of string here in the middle. I'll use this model to answer two questions. One, which should be relatively straightforward, is what happens if I cut this piece of string in the middle? So I cut this tiny piece of string in the middle. What happens to the system? Does the weight move up or down? And the second question we'll answer is what the hell does this have to do with networking? So I've brought the physical model here with me. It's the same as shown in the picture here with, of course, poorer craftsmanship. The weight doesn't even hang level. We should all just be thankful I don't build bridges or buildings. So right now, in this state, as shown in the picture, the weight in my configuration hangs at about 58 centimeters from the top if we think about its center of gravity. So I'll bring this closer so you can take a look. So the weight hangs at about 58 or 59 centimeters when we consider its center of gravity. And now what we'll do is cut that piece of string in the middle. So pause here and think for a moment, what do you expect to happen? So again, I'm going to be cutting this tiny piece of string in the middle here. And we want to see whether the weight moves up or down. So I encourage you to pause at this point and think about what you expect will happen in this configuration. 1, 2, and 3. All right, the weight moves up. Wow, isn't that something? So now the weight is at something like 51 centimeters above, hanging from the top, that is. So now let's get to the second question. What the hell does this have to do with networking? Let's set aside the physical model for a little bit and return to the network. In this example, we have a start node S and a destination T between which we want to move traffic through these two paths, SBT and SAT. Of the 4 edges in this network, 2 are load sensitive in such a way that the traffic on them determines their latency. So if we push X units of traffic through SB, then its latency is also X units. Of course, the units are different. For the traffic, it could be megabits per second or gigabits per second, etc., while the latencies are in milliseconds or seconds. The 2 other edges are load insensitive edges. So SA and BT, on them, latency is always 1 unit regardless of how much traffic we push through them. So in this setting, let's say we want to move 1 unit of traffic from S to T, and we can split it across these 2 paths. What should the optimal split of traffic be to minimize latency for all the traffic on average? With the symmetry of the situation, you should easily conclude that you should split your traffic 50-50 along the 2 paths, and that will result in a latency of 1.5 units for all the traffic. So you'll have 0.5 load on SB, that results in 0.5 latency. You pay 1 unit from BT, and that's in sum 1.5 units, and the same kind of thing on SAT. Now, let's modify this network such that we add a free link from B to A. Free in the sense that regardless of the amount of traffic on this edge, the latency is always 0. So now we have 3 paths in this network, the same 2 as we had earlier, SBT and SAT, the green paths from the previous picture. And then we have a new path, SBAT, on which the latency is 2x plus 0. So 2x if x is the traffic traversing the SB and AT edges. So let's start with the 0.5 split again. So we are not using the SBAT path right now. And let's see what happens if we move some traffic to that edge. Say we move epsilon units of traffic from both of the green paths to the red path. So now SAT carries 0.5 minus epsilon traffic, while SBAT carries 2 epsilon units of traffic. SBT also carries 0.5 minus epsilon traffic. So now on these X edges, the AT and SB edges, the amount of traffic carried is 0.5 minus epsilon for the one green path. So here the green path contributes 0.5 minus epsilon, and the red path contributes 2 epsilon. So sum total here is 0.5 minus epsilon plus 2 epsilon. So 0.5 plus epsilon is the load on this edge, and that's the same as its latency. So what are the latencies on the red and the green paths? On each of the green paths, you pay 1 unit of latency here, and you pay 0.5 plus epsilon here. So that's its latency. On the red path, you pay 0.5 plus epsilon, which is the load on this edge, plus 0 here, plus another 0.5 plus epsilon here. And that's the resulting latency. Now, if epsilon is small, green will be roughly 1.5 and red will be 1 unit. So the red path is better by 0.5 units in terms of latency for a small epsilon. But even as you keep increasing epsilon, let's say you make it 0.49 or even 0.499 and so on, as you tend towards 0.5, the red path is always lower latency than the green path. So if you're thinking of these individual infinitesimal pieces of traffic as drivers driving cars through this road network, then for every driver, there would always be an incentive to move from the green path from either green path to the red path because it provides a shorter travel time. And the equilibrium of the system is for all traffic to shift to the red path. Now what's the latency? So 1 unit of traffic traverses SB, 1 unit traverses AT. So the latency of all the not BA edges is 1 unit. So the latency end to end is 2 units. So now you'll notice that we've made the network worse by adding this free edge. The latency is 2 instead of 1.5 earlier. We could still use just the SBT and SAT paths and ignore this free edge in the middle and get latency 1.5. But because each of these drivers or units of traffic is choosing independently and selfishly, we end up with this undesirable equilibrium where everyone is worse off than they were before. This distinction between the two settings here is called the price of anarchy, the cost of making uncoordinated, selfish decisions, measured as the ratio of the network's optimal operation here, 1.5, versus the network's actual operation under selfish decisions, which is 2 units of latency. So 2 divided by 1.5 is the price of anarchy here. So now let's return and tie this back to the physical model we had. These two systems are actually identical. In the spring and string system, what we want to minimize is the latency equivalent, which is the extension of these strings with the weight hanging underneath the system. And on the S2T network paths, we want to minimize latency. The edges of the systems are analogous in this way. There's the springs, which are roughly linear in their extension corresponding to the force applied to them. So in some sense, their cost, which is the extension of the spring, is proportional linearly to the load added to them. And that's also true of our latency sensitive edges. There is a small piece of string in the middle here, which is our zero weight or zero cost edge, corresponding to this zero cost B to A edge in our network. And then there are fixed cost edges shown here, the fixed length strings whose extension does not depend on the weight added to them. And those correspond to the SA and BT edges in our network. So that's how the two systems end up being exactly the same. And the question of cutting the string here is the same as that of removing the free edge in the system, that is from B to A. And the conclusion is in both cases also the same, that the network is better off, or the spring and string system is better off in terms of its extension. Lower extension is better in this case. Both systems are better off without this free edge. So this is not just theoretical. This is well-studied phenomena called Braess's paradox. It has been seen in several road networks and computer networks. Road network examples are easier to find online. You can look at the Wikipedia entry and find several of them. In Seoul and New York, people observed that the removal of a road, closure of a road, sped up traffic through the cities, while in Stuttgart, the addition of a new road made the road network worse, causing a slowdown of traffic in the city. So now I want to leave you with this changed network setup where SNT have these two paths. One again is a constant latency path with 1 unit of latency on it. And the other path has latency that's proportional to the 100th power of the load added on that edge. So think about what the selfish equilibrium in this setting is. How much traffic do you move towards the bottom path versus the top path? And what is the price of anarchy that results from the selfish decisions versus whatever would have been the optimal split in this network? With that, the presentation is concluded. Thanks.